Now that we know about the heap and the stack, it's time to dive into a super important concept, which even if the rest is not interesting to you, you absolutely have to understand because it's super important for JavaScript, and it can be very confusing when you work with JavaScript when you don't understand this concept. It's about primitive versus reference values. Now, what is that? In JavaScript, we have two categories of types or of values, you could say. So with that, I don't mean strings and numbers, because that would be wrong. We also have booleans, objects, null, undefined, and so on. But I really mean these data types, which you already learned about. So booleans, strings, numbers, and objects, and so on. These can be categorized into two categories. We have primitive values and we have reference values. And that's an important differentiation which you need to understand. Now, primitive values are these 6 types of data. Strings, numbers, booleans, null, undefined, and symbol, which we haven't learned about, which we'll learn about later, which is very advanced, it doesn't matter right now. These are primitive values in JavaScript. So every number that you create and which you then store in a variable or which you use in a calculation is created by JavaScript or by the browser behind the scenes as a primitive value. Thus far, that didn't really matter to us, and in many cases it won't matter to you, but there will be one important difference to the reference values later. So it's stored in memory, normally on the stack, because normally these are relatively short-living, because JavaScript can get rid of them relatively easy. They're cheap to be recreated, so it can easily duplicate them. This doesn't cost too much. Not much memory is consumed by these values in the end. And therefore, they're typically stored in its stack memory. Now, if you keep that picture in mind where function calls are pushed on top of each other, remember that I called the stack a concept for managing execution contexts. Well, you could say each function there has its own execution context, right? The overall script has some global variables maybe, which are part of that anonymous execution context. Another function, which has an internal variable, has its own execution context. So primitive values typically are stored in the stack. I'm saying typically because they could be stored in the heap as well if it's a long-running operation. And in the end, it's the browser which decides which data ends up where. It actually doesn't even matter for what I'm explaining here. I just want to briefly mention it here that these primitive values are generally managed in the stack. More important to us, and the key difference between primitive and reference values, is that when you copy a variable, which means you assign it to a new one, which holds a primitive value, then the value is actually copied. Now, we took this for granted thus far, but the implication is quite important. If you open up your browser developer tools console on any web page you want, maybe the one we just worked on or a brand new one, doesn't matter. In there, if you create a variable with let, let's say you name it name, but that does of course not matter, you can name it however you want, and you store a value of max or any other string in there, then this obviously is a primitive value as you just learned. Strings are primitive values, and therefore, well, max is stored in there. If you now create another variable, another user, or whatever you want to name it, and you assign name as a value to that variable, then you're basically telling JavaScript, take the value stored in name and store it in another user. Therefore, another user, of course, also has max as a value. Now it gets interesting if we now change name to, let's say, manual. So we assigned a new value to that variable. If we now look into another user, though, we see that still stores max. And this kind of is what we expected and what we used thus far throughout the course. Whenever we took some value in a variable or maybe in a parameter of a function and we stored that in another variable, it was always clear to us that if we changed that original variable, the other variable where we stored it in would not change as well. And that's the case because primitive values are copied by value, which means when we do this assignment here, we're telling JavaScript and the browser, hey, take the value which is stored in name in this variable, create a copy of it, and store that copy in another user. Don't forget that all data, including strings and numbers, needs to be stored in memory somewhere. Now, as I said, typically that's the stack, and we don't have to worry too much about where exactly it is. But because it needs to be stored somewhere, it's not obvious or not something we could expect that JavaScript always creates a copy when we want to store it in a new variable. It could also just tell the variable, well, take that exact same value in memory, stored in the same place in memory, and store this address of that place in memory in the variable instead of the value itself. And if that would be the case, then changing variable 1 should also impact the value stored in variable 2 because they're effectively pointing both at the same value. But that's not what's happening with primitive values. Instead, there a real copy is created. So that's the behavior for primitive values. Now you can probably already guess what the behavior for reference values will be, but let's still have a look. What are reference values to begin with? Well, all other objects, or generally all objects in JavaScript. Now, technically, if you want to be really correct, string numbers and so on are not objects, but are dynamically transformed to pseudo objects, you could say, when you do something like name length. We haven't used that before in the course, but this gives you the length of the name, and with the dot notation, it kind of implies that we're accessing a property of name, which then in turn implies that name would be an object. But it actually isn't. It's a bit more complex than that, and we don't need to dive in all the internals here. But in the end, what happens here is JavaScript dynamically transforms a string or a number, so any primitive value, to an object temporarily if you use the dot notation on it. But other than that, it's a primitive value. And it's always behaving as you see it here on the left, no matter if you're temporarily transforming it or not. Now, all real objects, which always stay objects, are handled differently because they're more expensive to create, you could say. A real object, which you create on your own, or which might be built into the browser and exposed to you, like that moth object where we also called it the random function earlier in the course. Well, these objects, as you can imagine, hold a bit more data than just a couple of characters or just a single number. They're more complex to manage, and therefore creating them takes longer, occupies more memory, and so on. Therefore, the browser typically stores these in the heap, but again, the exact allocation logic is something the browser is responsible for, not you or JavaScript, but that's what the browser does. And important, a variable then only stores a pointer, so the address of that place in memory, and not the value itself. For primitive values, a variable really stored the value itself in it. For reference values, that's not the case, and instead the value is stored somewhere in memory, somewhere in the heap, and the variable stores the address of that place in memory, so a pointer at this place in memory, you could say. Therefore, if you copy a variable which holds a reference value, so if you assign it to a different variable, you only copy the pointer, the reference, and not the value itself. Now, what's the implication of that? Let's go back to the browser and reload. And now let's create a new array, let's say. And arrays are just objects. So here I have my hobbies array, which currently only includes sports. And now let's create another variable, new hobbies, or however you want to name it. And let's store hobbies in that by assigning it like this. Now, if we output hobbies here, we see that's the sports array. And new hobbies, of course, also is that same array. So thus far, you could think that the value was copied. Now let's actually go to hobbies, so to the original array, and push a new element onto it. Let's say cooking. So this new string is pushed onto hobbies. So if now I output hobbies, I of course get that array with sports and cooking. But as you now probably expect, new hobbies also includes cooking, even though we never touched new hobbies. But it includes this value because when we assigned hobbies to new hobbies, we only copied the pointer. We only copied the address of that array. So the element itself, the value, the array itself was never duplicated or copied. Instead, we only copied the address. And that means if we change one array, we automatically change the other array because there is nothing like 1 in the other array. There only is exactly one array in memory, and then both variables hold the same pointer at that place in memory. It's the same for objects, by the way. If we have person here, and this person, let's say, has an age of 30, and then I have another person, and I assign person to that. If I then, to mix it up, go to another person and set the age here to 32, then if we have a look at person, we see there the age changed as well, for the exact same reason. Now, what can we do about that? Well, in general, you don't need to do anything about that. That is a default behavior for a good reason, to avoid unnecessary duplication of data, to avoid cluttering your memory, to be more efficient, provide better performance, and so on. But of course, you sometimes have cases where you need to copy data, where you need to store it somewhere else, and where you want to make sure that if you edit the copied, in quotes, because you're not really copying it, so when you're editing the copied data, that the original data isn't. Now, we'll have a closer look at solutions in the arrays and objects deep dive sections, which will come soon after this one, where I explain a bit more about the solutions and how they work. For now, I'll just quickly show them to you, and we'll dive into the details later, because right now we don't really need that in the course, but I also don't want to hide that solution from you right now. So let's say we now want to create a real copy in yet another person in this variable, and there I want to copy person. Now, as you learned, like this, it wouldn't work. Now, you can use a different syntax, where you create a new object with curly braces, right? This creates a brand new object. And if you do so, then you can add a brand new operator, which we haven't used before and which I'll cover in more detail in the objects and arrays sections I just mentioned. It's 3 dots, which looks rather strange, but this is a operator built into JavaScript. It's called the spread operator. And after that, you can add person. Now, what this operator does is it pulls out all the key value pairs in person and adds them as new key value pairs to this new object. And since this is a new object, it's a real copy. It's a new place in memory, new address. The old person also still is there, but this also is now a new object. So if we do that, then yet another person, of course, has the age of 32. But if we now change person age back to 30, you'll see yet another person still has an age of 32 because now this was a real copy. Now for arrays, a similar approach exists. If we have our hobbies here with sports, and then we have more hobbies and we want to create a real copy, then we create an empty array, use that same spread operator, so the 3 dots, and then that existing array, and now just as it pulled out the key value pairs for the object, here it basically pulls out all the elements of the array and adds them as elements to this new array which we create with the help of the square brackets. So therefore now, if I go to hobbies and I push cooking as a new hobby onto that array, you'll see that more hobbies still only has sports. Again, that's the quick introduction to that solution. A closer look at the spread operator will be taken in the arrays and objects modules. So now that we covered reference and primitive types, we can also dive into something else, which I already showed earlier, but where we had no great explanation of why that was happening. I'm talking about a use case where we have maybe a person, let's name it person 1, where the age is 30, and then another person 2, where I don't assign person 1, but I instead create another new object with curly braces, where the age is also 30. So to us, these are exactly the same objects, and still, if I perform a Boolean comparison here with either 2 or 3 equal signs, doesn't matter, you see the result is false, so they're not equal. Well, now this makes a lot of sense. Keep in mind that what we actually store in person 1 and person 2 is a pointer at a place in memory. And these are 2 totally different objects, even though they hold the same data, but they are 2 different distinct objects stored in different places, so at different addresses in memory. And since person 1 stores the address of this object, and person 2 stores the address of this object, and these are 2 different objects, we have 2 different addresses. And therefore, if we compare person 1 to person 2, what we effectively compare is whether the address of person 1 is equal to the address of person 2, and that is not the case. This is why we get this false result here. This is why they're not equal, because of that reference type thing. And it's the same for comparing arrays. Another important implication, which also can be confusing when you work with reference types, is this one. Previously I created hobbies with let, right? Now here's something which might confuse you. If I create it with const hobbies, and I have an array there which includes sports and nothing else, then let me try to push something onto hobbies. Let's say cooking. Would you expect that this works? Keep in mind that it's a constant, so we can't change the value after it has been created. Well, you might expect an error therefore, and yet if I hit enter, we get no errors, and if I have a look at hobbies, we see cooking was added. So how does that work? Well, again, keep in mind, this array gets created somewhere in memory, and what's getting stored in hobbies is the address of that array or of that object. Arrays are objects, as you learned, so the address is getting stored in this constant. Now, when we call push, we certainly do manipulate the data in memory. But what do we not manipulate? The address. It's still the same address. The data in memory changed, but it's still at the same address. Maybe more memory was allocated to it. That's something the browser does. But we don't care. We don't care if more memory was allocated. The address is the same. So in this constant, the value never changed because the value is the address and the address didn't change. Just the data behind the address, but that's not what's getting stored here. Therefore here we can change this like this without getting an error. It's different if we try to assign a new array like this here. Sports, running. If I try to do that, I will get an error. Why? Because we use the equal sign here, and that means we try to assign a new array. Now, of course, as you learned, the array will never really be stored in there, but what matters is that we do indeed create a brand new array here, which means a brand new place in memory, a brand new address, and therefore JavaScript tries to store a brand new address in hobbies. So now the value of hobbies would get changed, and that indeed is not allowed because it's a constant. So using constants with a single equal sign to assign a new value is never allowed. But changing the objects which might be stored in them, that is allowed as long as you use something like push. Now, of course, you can't change primitives stored in constants because these are not stored in memory and there is no address stored in the constant, but instead the real value is stored in it. But for objects and arrays, this works. So just to also give you an object example, if person would be stored in a constant and I set the age to 30, I can of course output it, but I can also access the age and set it to 32. And if I now output person, this would work because now I only change the data in memory. You could argue that I am using the single equality operator, so the assignment operator here, but I'm using it on age, not on person, right? I'm not saying person is equal to something. That would fail. If I set person to a new object, this would fail. But I'm setting age inside of the person to a new value, not person itself. So I'm only setting a part of the data stored in memory to a new value, just as we did it with the array a second ago. And therefore, the data in memory certainly changes. The address does not, and therefore the address stored in the constant person also does not change. I'm really emphasizing this because it is such a crucial concept and that can lead to a lot of confusion. Constant arrays and objects which suddenly change are a common source of confusion, and the same is true for data which you change in place A and it suddenly also changes in place B, because people forgot or never were aware that there is something like reference values, which really matters a lot because it explains all that behavior. So this is a must know when you work with JavaScript, and I hope that these lectures really made it clear what primitive values and reference values are, how they work, how they behave, why they are important, why they are useful, and how you work with them.